In 2025, oil fields around the world burned 167 billion cubic meters of natural gas. That was roughly equal to the amount consumed across the entire African continent during the year, with an estimated value of $54 billion. Instead of generating electricity, heating buildings, or supplying factories, this gas disappeared into flames burning above oil fields and processing facilities. Natural gas is traded across international markets, transported through enormous pipeline networks, and cooled into liquid so it can cross oceans aboard specialized ships. Yet at many oil fields, the same fuel is deliberately routed into flare stacks and burned without producing any useful energy. So where does this gas come from? Why can't an oil company store it or sell it alongside the oil? And why does keeping the oil flowing make burning the gas the more P2 profitable choice? Crude oil and natural gas often occupy the same underground reservoir. Under high pressure, some of the gas remains dissolved in the oil, while additional gas collects above it. As the mixture rises through the well, the pressure falls and the dissolved gas separates from the liquid, much like carbon dioxide escaping when a bottle of soda is opened. At the surface, the well stream enters a separator. Water is removed for treatment or disposal. Crude oil flows toward storage tanks or an oil pipeline, and the gas leaves through a separate outlet. Because this gas is produced together with the oil, it is known as associated gas. From this point onward, the two products require completely different systems. The oil can remain in a tank until a truck arrives or space becomes available in a pipeline. The gas cannot remain inside the separator. As long as the well keeps producing oil, more gas continues entering the surface equipment, and the operator must move it somewhere to prevent production from stopping. Unlike the oil, however, this gas cannot simply be placed in a tank and collected later. Before anyone can buy it, the operator must first process it and build a continuous route from the well to a customer. Crude oil becomes commercially useful with relatively little preparation. Once water and sediment have been removed, it can be stored in a tank, pumped through a pipeline, loaded onto a truck, or carried across an ocean aboard a tanker. Natural gas cannot be moved so easily. Gas from an oil well often contains water vapor, carbon dioxide, hydrogen sulfide, nitrogen, and heavier hydrocarbons. Water corrodes pipelines and forms solid blockages under certain temperatures and pressures. Hydrogen sulfide is toxic and corrosive. Other components alter the gas's heating value. Before a pipeline operator accepts the gas, treatment equipment must remove enough of these substances to meet the network specifications. The treated gas must then be compressed. Gathering pipelines carry gas from individual wells to a central processing facility, and larger compressor stations push it into a transmission pipeline leading toward power plants, factories, cities, or an export terminal. The gas only becomes a saleable commodity after this entire route connects the well to a customer. In a mature producing region, much of that system already exists. A new well only needs a gathering line to reach a nearby processing plant. A remote oil field starts from nothing. The operator needs pipelines between the wells, compressors, treatment facilities, land access, permits, and a connection to a market that consumes enough gas to justify the investment. A pipeline by itself does not solve the problem. It must end somewhere that needs the gas. An oil field hundreds of kilometers from a major industrial area, electricity network, or export terminal cannot earn money from its gas simply by placing it inside a pipe. The gas therefore has value, but only after a long and expensive chain has been built around it. Until that chain exists, the operator still needs to handle every cubic meter reaching the surface. If a pipeline is not ready, storing the gas appears to be the obvious solution. The problem is that natural gas occupies far more space than crude oil. Oil is already a dense liquid at ordinary temperatures and pressures, so a steel tank can hold thousands of barrels without refrigeration or extreme pressure. Natural gas must be forced into thick, high-pressure vessels, which are expensive and hold only a limited amount compared with an oil tank of similar size. The gas can also be converted into liquefied natural gas. Cooling it to approximately minus 162 degrees Celsius reduces its volume by about 600 times. But doing that requires gas treatment equipment, powerful refrigeration systems, cryogenic storage tanks, and dedicated loading facilities. These systems are built for large, stable gas supplies that will operate for many years, not as temporary storage beside a few oil wells. Storage can absorb a short interruption, but it cannot solve a continuous production problem. The wells produce more gas every hour, and once the available storage is full, the operator must either stop producing oil or provide the gas with another permanent destination. When the gas has nowhere to go, it cannot be allowed to accumulate inside the equipment. Pressure rises until the well or processing unit must shut down, while releasing unburned gas around the facility creates a flammable cloud near engines, electrical systems, hot machinery, and workers. A flare gives the gas a controlled outlet. Pipes carry it away from the main equipment to a raised stack, where a pilot flame ignites it. The same system protects the facility during a power failure, compressor shutdown, blocked pipeline, maintenance operation, or sudden pressure increase. Pressure relief valves send the excess gas to the flare before it damages pipes, tanks, or processing equipment. This is why even facilities that normally capture almost all their gas still need emergency flares. Routine flaring begins when that safety system also becomes the normal destination for gas produced during everyday operations. Burning the gas is also less damaging than releasing it directly into the atmosphere. Natural gas consists mainly of methane, which traps approximately 27 to 30 times more heat than the same mass of carbon dioxide over a 100-year period. Combustion converts most of that methane into carbon dioxide and water. Flaring still produces carbon dioxide, soot, and other pollutants, and some methane escapes when combustion is incomplete. The International Energy Agency estimates that average global flare combustion efficiency is about 92% when poorly operating and extinguished flares are included. Even so, a functioning flare releases less methane than direct venting and allows the oil wells to continue producing. That explains why the gas is burned instead of released. It does not yet explain why the operator accepts the waste instead of building the equipment needed to sell it. The estimated value of flared gas is based on the price it could command in a functioning market. The producer does not receive that price at the wellhead. Before the gas reaches a customer, the company must treat it, compress it, transport it, and operate that system for the remaining life of the field. Whether the investment works depends first on the amount of gas being produced and how long that production will continue. A large field delivering a steady flow for decades can support a processing plant and pipeline. A small group of declining oil wells cannot generate enough gas revenue to recover the same cost. Distance and gas quality add to the expense. The operator therefore compares the value of the gas being burned with the oil revenue lost by keeping the field closed. When the oil is worth far more than the gas, waiting for the pipeline destroys more value than flaring. This is why $54 billion of flared gas does not represent $54 billion of available profit. That estimate reflects the gas's value after it reaches a market, before subtracting the cost of building thousands of separate routes from remote wells to customers. At the wellhead, the flare costs less, starts operating immediately, and keeps the higher value oil flowing. The best way to avoid routine flaring is to plan the gas system before oil production begins. Several nearby fields can share gathering pipelines, compressors, a central processing plant, and a connection to the transmission network. Combining their output creates enough gas volume to support infrastructure that none of the smaller fields could finance alone. Where no pipeline exists, the gas can be used at the field. CNG and small LNG systems provide another option when the gas flow is large and stable enough. Compressing or liquefying the gas makes it dense enough to transport by truck. But the additional equipment only pays for itself when production continues long enough and a customer exists within an economical distance. Every alternative, therefore, depends on the same basic conditions: enough gas, enough remaining field life, a practical destination, and a use valuable enough to recover the investment. When those conditions are absent, installing a different technology does not automatically make the project profitable. These alternatives become much more attractive when governments limit routine flaring or charge companies for the gas they burn. Once flaring itself carries a significant cost, pipelines, reinjection systems, and other recovery projects that previously looked uneconomic can begin to make financial sense. That is how natural gas worth billions of dollars can still be cheaper to burn than to sell. Thank you for watching. If this video changed the way you see the flames burning above oil fields, please like the video and subscribe to the channel for more stories about how the systems around us actually work. I'll see you in the next video.